because there is a mezzanine. Okay, so today we end this course with a topic called thin wall pressure vessels. What is a thin wall pressure vessel? May I ask you to give me a piece of page, please? Just give me a piece of page. If you have any rough page. So a thin wall pressure vessel is actually a vessel or a conduit which is transporting some liquid from one place to another, but that vessel is having very thin walls, as the name suggests, very thin walls, okay, to transfer some fluid from one place to another. That is your pressure vessel. And what our aim is to find out the stresses in the pressure vessel. Now, imagine I have this pressure vessel, which looks like this. And imagine it is transporting some water. Okay, so water is flowing in this vessel. Now, what will happen if this joint is not strong enough? If the water is flowing through it, and if fluid is flowing through it, we know from our fluid mechanics that all the liquids, they have got equal pressure in all the directions, and that is normally normal to the surface. So the liquid or the fluid will induce normal pressure onto this vessel. Okay, and as a result, what will happen is that this vessel will try to open up. Okay, so our aim is to have this joint strong enough so that it can transfer the fluid from one place to another. Okay, this joint is called longitudinal joint. Okay, so what we do is normally either we weld this, okay, or either we put some material around it so that it's strong enough so that it is attached strongly and it doesn't open up. Okay, so you put some material like a belt or something around it, wrap something around it so that it doesn't open up. Okay, so our aim is to find out the stress, the limiting stress which you can apply to this sort of structure, which is pressure vessels. Okay, so that is one type of joint in a pressure vessel. But what happens, there can be another scenario where your pressure vessel can be closed at one end, okay, like a cylinder. It can be closed and you can put water in it. Now the water, okay, what will happen is the water, since it apply pressure equally in all direction, so obviously it will try to open up this one. But if I have put a cap at the bottom, that cap will also try to come off. Okay, so that cap has to be strong enough to take the load of water. Okay, so the water can be this structure can be vertical or this can be horizontal, it doesn't matter. But the important thing is that if you close it, okay, if this vessel is closed, like for example, you can have such sort of vessels in industry. Okay, in petrochemical industry it's very common, but mechanical engineers normally deal a lot with pressure vessels. Okay, so you can take an example of a fuselage of an aeroplane. The fuselage is also like a vessel. okay, and that also has to sustain some load, okay. So our objective is to find out the limiting stresses in such sort of vessels, okay. So everything comes down to stress is equal to P by A. It's nothing complicated, but you just have to see which are those areas which take the load, okay, which are those areas which resist the load. Like if we have got a beam, okay, you try to apply a load, beam will try to bend. So you know that this beam, the beam should be strong enough or stiff enough to take the load. That is the resisting load or resisting moment. Okay, it should be strong enough to take that resisting moment. Similarly, in the case of thin wall, in the case of pressure vessels, it should be strong enough to take the applied load. And there are places which take the load. Okay, and we will see that in a minute. But before that, I would like to emphasize on one thing, that in thin wall pressure vessel, that thin wall pressure vessels are those vessels where your thickness is less than the diameter, the 20th of a diameter. Okay, so if that is less than, if the thickness is less than 20th of a diameter, then those structures are called as thin wall. Okay, we did thin wall structures when we were doing shear flow in thin structures. So I gave you lots of shapes, Z shapes, W shapes, and all those. They were thin wall. Okay, so in the case of spherical or round structures, we have this condition, that thickness, which is the thickness, the wall thickness, that must be less than the diameter, than 1/20 of a diameter. Okay, so that is one condition. Now imagine it's the same vessel which I am carrying, okay, and there is fluid running through it. What happens is that you have all the fluid, the pressure, which is equally distributed all around. Okay, and what is that part which take all this load? It is the walls. Okay, so if your water is flowing through it, it's the walls which take all the load. So you have to make sure that the walls are strong enough, okay, to sustain that load. If the walls are weak, what will happen? The walls would be ripped off. The whole, okay, so that is something which you don't want. You don't want them to be in tension, to fail in tension. Okay, so in a thin walled pressure vessel, the important thing is that you have got all the load, which is, we consider half of the vessel. Okay, so you have got all this load, and this is the fluid pressure. The fluid pressure has to be resisted by the walls. Okay, so that is an important thing to appreciate. The fluid pressure will be resisted by the wall, as shown over here. Okay, these walls are actually taking this the fluid load. Okay, the walls should be strong enough. Okay, so it is like, for example, I'm trying to carry a chair in a sheet, in a big cloth. Okay, so I have a cloth and I lift the chair through my cloth. Okay, or in other words, I'm trying to lift something. Like, for example, I've got this eraser. Okay, and this is my vessel, and the vessel, it's the walls which should be able to take that load. If I put very heavy structure over here, what will happen? The walls would fail. It will fail in tension. So if I put a very heavy piece of rock over here, then there is a possibility that the wall will fail. Okay, so it's the same thing, same philosophy, that the thin walls should take the load. So what we do is, what we do is, since this load is distributed uniformly, so that tells us that we have to integrate the whole thing. Okay, all this load, all the load has to be integrated. So what happens is that we have got a differential force, a small force. We take a small area. Okay, so imagine I take this load and it is applied on a small area which is shown in red. Okay, so this is that area. It is, so this area is r d theta because it's making a sector of a circle. It's r d theta, and we say that this sector is at an inclination theta from the centroid. Okay, so we have got this area and we are trying to find out the pressure on this area. So what is that pressure? Pressure is P times dA. That's pressure. That's the force. Okay, so the force on this small infinitesimal area is pressure, the fluid pressure, times dA. And what is dA? dA is r theta. R theta, which is d by 2 theta, times the length. So this is the whole length. So in other words, what we are saying is, imagine this is fluid which is in this vessel. So what we are saying is that we take a small strip of this which is shown as dA, okay, and we say that this dA is equal to r, imagining that this is actually a semicircle, r times theta, d theta, okay, so which is d by 2 times your theta, okay, and times the length. This is the length, okay, so that is equal to r pressure times L times d by 2 d theta. Okay. This one has made a mistake. This is d theta. So, and this is d. Okay, so d by 2 times r d theta and times L. That is the area which is subjected to this pressure. Okay, now what we do is we take, so this is the same equation written again. Now what is the total force? The total force is this semicircle. Okay, so we integrate this from 0 till pi. Okay, but we take sine theta, sine component of this one. Why are we taking sine component? Because we are trying to find out the force which is vertical. Okay, so we are trying to find out the force which is vertical, and it will be the sine component of this guy which will be resisting that force. Okay, the cos component doesn't contribute. So what we are doing is, I am saying that we have got again this pressure vessel, and this pressure vessel has to resist the fluid load, okay, through walls. Okay, so the walls are actually resisting the fluid load, and the walls forces are vertical, are facing upward. So we take all this pressure which is over here and take the vertical component of that. So summation of, we can apply the summation of Fy or F vertical equal to 0. Are you guys with me? So we are just applying summation of Fy equal to 0. Why? Because we are taking semicircular vessel. Okay? And the force, the resisting force is facing vertically up. If this was facing in this direction, for example, not vertically up, then we would be taking the cosine component also. Okay? But the cosine component we say is 0. Why? Because there is no force which the cosine component can take. Normally the cosine component will cancel out. Okay? So the cosine component of these forces, they will cancel out. Summation of horizontal forces is equal to 0. It's only the vertical component which is actually resisting the, applying the load. Okay? So what I said is that we have this small portion, small sector on which there is a pressure P applied. Now this pressure P, the pressure P is actually the pressure imposed by the fluid. This pressure P has two components. One is in vertical direction, another one is in horizontal direction. The horizontal direction component will cancel out with the same sector which is on the other side. So the horizontal components, they cancel out. Okay, all the horizontal force, okay, will cancel out with the other side. The force which is remaining, that is the vertical one. And that vertical force we find out by taking the sine component of this. Remembering that with respect to the axis, we have angle theta being made by this reference sector. Okay, so that is something an important, that's important thing to appreciate. Now once this is done, then the rest is just algebra. Okay, we integrated 0 to pi, the rest is algebra. You get minus cosine theta from this integral, and then f is equal to p dl. Now this is a very interesting formula, and this formula you will come across again and again in mechanics. Okay, what does this formula say? It's saying that your vertical force is equal to P, which is the pressure, okay, times dl. Now dl is the area. This is the horizontal projection. dl is the horizontal projection of this vessel. Okay, horizontal projection of this vessel. D times L. The vessel area is how much? Pi r square by 2. Okay, and then times the length. That's what the vessel area is, isn't it? Pi r square by 2 times the length. But this equation is telling us that it is the component dl. If you multiply dl with the pressure, that will give you actually the resultant load. You don't have to multiply pi r square by 2 times L. You just take the horizontal projection of this vessel, and you will get the vertical load. So this is a very helpful formula. Okay, this formula will be used again and again, especially when you are doing steel structures and when you are studying the bolts inside a hole or a rivet inside a hole. Okay, and that is applying pressure. So what I'm saying is the application of this formula is in one of the application of this formula is in a bolt which is in a hole. Now what happens to this ball? Now imagine I've got this hole and there is a ball over here. Now what is happening? This, when the ball is resting against the wall, okay, of the hole, and when I apply pressure, okay, I'm applying a pressure onto the wall. The hole is actually circular, isn't it? And I'm applying pressure onto the wall. So that pressure, if I multiply with the vertical projection of this wall, vertical projection, that will give me the overall pressure in the hole. Okay, so I mean, although this is applied to the vessel, it is equally applicable to bolts in a hole. Okay, so for example, if you have got two planks which are nailed to each other and you are trying to pull them apart, okay, it's the same thin wall pressure vessel formula which you have to apply, okay, in order to get the pressure on the hole, because obviously you don't want the hole to become so weak that the screw or the nail, it comes off. The main idea that you have nailed the two is that they both stay together, isn't it? So when you are trying to work out your number of nails, okay, which will take the applied load, you have to make sure that you find out the pressure, and that pressure is manipulated in such a way that you find out the load resisted by one nail. And I'll tell you how that works in the case of pressure vessel. But my point is that this formula, force is equal to pressure times dl. This makes our life very easy. Why? Because we don't have to take the round area, the surface area of the vessel. We just take the horizontal projection, which is dl, multiply that with the pressure, and we get the load in the walls, the load resisted by the walls. Okay, so once this is done, after this we can write that this total pressure is equal to 2P, because we have got two walls. 2P is equal to P dl. We can write that summation of Fy is equal to 0. So we have 2P is equal to F dl. F dl. After this, we can divide this P by the area of this wall. Okay. So what is the area of this wall? Thickness T times L. That is the area of this wall. So we can divide this F. Okay, so we can take the force by area, which is what? P dl, okay, by 2 divided by thickness times L. So this force is